Hello, hello. Can you guys hear me in the back? Can you guys hear me in the back a little more? What about now? Hear me in the back, okay? All right. Welcome to Data 8, Lecture 3. Today we're going to be talking about expressions and introduction to Python. I'll start off with some announcements. So the first announcement that I have is that you may have noticed some horrible noises coming from the back area of Soda. That's because when Soda was first built, they did not construct the waterproofing correctly, so that now lots of water is leaking into the basement of Soda, and it's just a terrible disaster. And so what they decided to do for us this summer is fix up Soda Hall, which unfortunately means that for the next couple of weeks, we just have to deal with horrible noises, horrible smells, horrible everything. So I hope that you guys will be patient. I'll try to talk a little louder, but if you guys can't hear me or have trouble, just raise your hand or go like this or something to let me know, okay? For those of you listening to the recording, I'm sorry. I can't do any much about it. I also want to let you guys know that my office hour times have been changed. So instead of Monday and Tuesday office hours for me, I'm going to be having my office hours Tuesdays from 1 to 2 p.m. and Thursdays from 3 to 5 p.m. So that includes tomorrow. So if you want to come ask me about something or you have something logistical you want to work out with me, I'll be in 258 Corey tomorrow from 3 to 5 and from then on Tuesdays and Thursdays. Finally, for those of you who do not have @berkeley.edu emails, I should have sent you guys your calendar ID and berkeley.edu emails yesterday night. If you did not receive an email from me about that, you should go on Piazza, fill out that form that we said to fill out if you didn't have a berkeley.edu email, and then email me about it, letting me know that you don't have a berkeley.edu email, because you need to do homework 1 as well as lab 2 for today and tomorrow. I want to start off today by reviewing the stuff we did yesterday. So we covered a lot of different topics, a lot of different vocabulary yesterday, so I want to just make sure that we're all on the same page, that we have everything down, that we feel good about what we did yesterday. So when we're trying to compare or when we're trying to establish cause and effect, we have our study individuals, which are the people or the things that something is happening to. We group them by a treatment, and then we measure the outcome of that treatment. Yesterday, we talked about the simplest case, which is where we have a treatment group where something happens, and a control group where something doesn't happen. And what we said was, if the outcome differs between those two groups, then we say that there is an association or any relation. If you recall, yesterday I used the example of eating chocolate and heart disease. So people who ate chocolate died at a lower rate of heart disease than chocolate abstainers. And we said that because just the percent of people who died of heart disease differed between the two groups, there was an association. But we did say that association is not the same as something causing the outcome to happen. And to establish causality, we need an additional constraint on our two groups, which is that we need our two groups to be similar in all ways except for the treatment. Only then can we say it was our treatment that caused the outcome and not something else. So we give a name to that something else that might cause an outcome. We call it a confounding variable. And what happens is, if our two groups have differences and we haven't done our part to try to minimize those differences, then we can't say for certain whether our treatment was the one that caused the outcome or one of those differences was. We call them confounding factors. And I wanted to make sure that we were clear on the vocabulary we used yesterday, which is the difference between observational studies and controlled experiments. So I got a great question about this from someone yesterday, and I realized I could have been more clear about it. So to be very clear, an observational study, so in both cases we have two groups, a treatment group and a control group. The difference between the two things is whether we get to split up the individuals into two groups and whether we get to administer the treatment or not. So in an observational study, we don't get control over the individuals in our study. we can only, so the individuals themselves have separated themselves out into 2 groups, and something has happened to them, but we have not done anything to the individuals there. For example, we want to know whether wearing gray shirts makes you look better, okay? And so, for example, in this classroom, I see some people with gray shirts. You guys look great. Get it? Great. Okay, so, so in this classroom, people are wearing gray shirts, and we can measure, or we can have some measure of how good they look or how good they think they look. And in that case, we would call that an observational study, because I did not choose the people with gray shirts. I did not give gray shirts to those people to wear. They just came into class. We just came into class today. We wear gray shirts. We happen to look good. Okay, fine. On the other hand, if I were running an experiment and I was trying to determine whether wearing gray shirts makes you look better, the right thing to do would be to split up the classroom and I would give some people gray shirts and say, wear this gray shirt, and then I would measure how good they look or how good they think they look when they're wearing the gray shirt. So I hope the difference is clear there. So observational study, I don't get to administer the treatment. It just kind of happens. I observe it. A controlled experiment, I'm the one giving the treatment. I'm the one splitting the 2 groups up. There's some system that I have designed in order to see the effect. Any questions about that? All right. So the reason why, so in the previous slide, I note that observational studies tend to have confounding factors or some differences in the 2 groups. The reason why they have those differences is because we don't get to randomize people into 2 groups in an observational study. Randomization actually allows us to kind of minimize the differences between the 2 groups, because if we randomly assign people to 2 groups, chances are pretty good that the 2 groups will look similar. The important thing about randomization is that if we do it properly, we can actually account mathematically for the differences between the 2 groups. And that allows us to actually say, okay, well, how do I think about my conclusion? Is this an actual valid thing to say? Because of this, randomized controlled experiments to data scientists are one of the most reliable ways to establish causal relations. So typically, these are the standard practice used in medicine, used in all sorts of different fields. We like randomized controlled experiments because we can say with more certainty that our treatment caused the outcome, not something else. All right. Any questions about that? Cool. Let's move on. So today we're going to be switching gears a little bit. We're going to be spending the next couple of lectures talking about programming in Python. Today we're going to be talking about expressions, the building blocks of Python. And as I mentioned before, we chose Python for this class because it's popular not only in the data science world and the academic world, but also in industry, in companies, and people just generally like this language. It also happens to be easy to learn, so it's a win-win-win for everyone. The thing about learning a programming language, especially for those of us who are learning a language for the first time, is that it's pretty hard. If you guys went through lab 1 and you're like, what is going on? Like, I don't understand why stuff is breaking. Then you feel my pain. And learning a language is pretty hard. It requires a lot of effort and practice. Unfortunately for us, once we learn a language for the first time, learning other programming languages becomes a lot easier. So you kind of have to like work through it and practice a lot and kind of just figure out how this language works. But once you do that, life gets a little easier. There's a little bit of a learning curve at first, but hopefully with enough practice and with enough help from your peers and from us, you'll get the hang of it. The thing about learning Python also is that it's definitely better to practice yourself instead of listening to me stand up here and talk at you. Unfortunately, I'm standing up here and talking at you, so this is what we'll have to work with for the next couple of days. But I do encourage you to follow along with what I'm doing today at data8.haas.berkeley.edu. So I'm going to be switching over now to data8.haas.berkeley.edu and programming in Python, and I'm going to be pointing out some stuff that you guys should be aware of. The reason why there's Haas in the URL is because the Haas School of Business has graciously allowed us to borrow their computers for this class for this summer. And so because of that, they wanted the branding in the URL. So shout out to Haas. All right, switch here. I just want to point out something that you guys may have noticed. So you guys notice that if you log into Data Hub, I'm going to call this Data Hub or Jupyter Hub. I'm using terms interchangeably, just depending on what I feel like. So if you log into Jupyter Hub, you'll notice that there's a button here called Start My Server. What you want to do is you want to make sure you click that button before you click a link to pull in a homework or a lab. If you don't do that, you might not get the homework or lab the first time you click it. So just make sure you click that button, Start My Server, and then go to data8.org and get your lab or get your assignment or whatever. In this case, I'm not going to go there because I'm just going to make a new notebook. All right, cross section 3. All right, so you guys should have seen so far in lab that you can do some basic calculation in Python. Okay? So I can do 2 plus 3. Great, I can get 5. 2 times 3. I get 6. Okay, so pretty standard. It feels like a calculator in this aspect. However, Python is very picky about how you write your expressions. All right. So if I happen to write 2 times 3, it will give me something called a syntax error. Okay, so you get some color text, red text. It's very scary. But if you read what it says here, it says invalid syntax. Syntax just means that you wrote your Python code that in an invalid way. Okay, so it didn't even try to run my 2 times 3. It just said, this doesn't look like Python code to me. You should fix it. So syntax error means invalid syntax. So you can't have two multiplication signs with space in between. However, if you happen to do 2 multiplication signs in a row, this is the exponentiation operator. Okay, so right here I've covered. So right here is addition. This is multiplication. In Python, when you want to take something to the power of something else, you do times. So I can do 2 times 4, and I get 16 because that's 2 to the power of 4. I can also do division. And what you notice when I do division is that I get numbers with a decimal place. I'm going to be covering that later, but just know that when I do division, I'm always going to get numbers with a decimal place. I can also try to divide by 0, because why not? And I get an error. The error says 0 division error, division by 0, because I tried to divide by 0. Thank you, Python. And it's different from the error that we got before. So let me show you the difference here. So this is called a syntax error. A syntax error means the Python code itself is bad, and Python didn't even try. It said this doesn't look like Python to me. A 0 division error means Python says your code looks good, but when I actually tried to do 2 divided by 0, I ran into a problem. Okay, so 2 types of errors here. Just remember that if you run into a syntax error, you should check your code out to see if you structured it properly. If you miss a parentheses or you put spaces randomly, like that might cause a syntax error. Other types of errors are caused by your code. So that means that your code, Python tried to run your code, but there's something went wrong with the process. Okay, so syntax error, other types of errors. Python, like graphing calculators, will also follow the rules of like the operator order of evaluation. So if I do 1 plus 2 times 3 times 4 times 5 divided by 6 times 3 plus 7 plus 8 minus 9 plus 10, what you'll notice is that I get 17.55 because what happened was the exponentiation happens first. So this is like divided by 18, and then the multiplication happens. And then I do the addition and subtraction. So I get 17.55. If I want to make sure that some things happen before other things, then what I can do is I can put those things in parentheses. So if I put parentheses here, I have to make sure that the parentheses are closed. So if I just put one open parentheses and don't close it, I'm going to get another syntax error. Okay. So I'm going to close the parentheses here. And what that tells Python is run this stuff first, and then do the exponentiation, and then do the multiplication, division, and then do the additions and subtractions. And if I do that, well, happy New Year. All right. Go back to the slides. So to just recap quickly what we've done so far, we've gone through some basic arithmetic operators. There's one more operator that I haven't demoed for you guys today, which is the remainder operator. It looks like a percent sign. It just takes the remainder after you divide a number by something else. So if you see a percent sign, we won't use it too often in this class, but if you see a percent sign, just know that it's the remainder operator. So those are some basic, that's how to do basic arithmetic in Python, and now you can use Python as a calculator in case you don't have a graphing calculator. Cool. So I want to run through an example about slopes. So here's a visualization of income of doctors versus other professionals. I think the person who made this visualization really wanted to show that doctors make a lot more than everyone else. I show this visualization also because it's an example of what not to do when you're making a visualization. So for example, they have lots of heads, and the heads on this graph here are very unnecessary. You do not need to put heads on your graphs. Okay? The heads here are also unnecessary. Don't put heads there either. And it's also misleading because if you look at the x-axis here, the years are not actually evenly spaced out. Okay, so this is 1939. Here's like 1947, which is 8 years later. But then it goes to 1951, which is just 4 years later, and then here, like 1973, is only 1 year before 1974. So this graph is kind of wrong in a lot of ways. And if you want to actually make this graph okay, what you would do is you would do something like this, which is boring, but it actually conveys or communicates what this graph is actually trying to show originally. So here we have the years and the x-axis actually spaced out properly. We've taken all of the bars here and kind of plot them as points and drew a line between them, so you can actually see the trend instead of having to look at strange floating heads. And what you can see there is that there's actually kind of two regions of this graph, right? So we have kind of this region right here where doctor salaries are going up, and then something happened in 1965-ish, and all of a sudden doctors are starting to make a lot more every year than other professionals. So this graph makes it look like the salary for doctors just increases linearly, but this graph right here shows something different. And what we can do is we can calculate the slope in the first part of the graph, and then calculate the slope in the second part of the graph. Okay, so to do that, it's fairly simple if you recall your high school algebra. So what I'm going to do there is take a look at the points and do difference in height over difference in x-axis. So difference in y-axis over difference in x-axis gives me the slope. So I'm going to go ahead and calculate the slope for those two parts of the graph. So the first part of the graph, doctors are making about $25,000, and in the beginning of the graph, they're making about $3,000, and I'm going to take the difference in x-axis, so 1963 minus 1939, and I'm going to run that, and I get $23,000 of increase per year. And you look at that and you're like, does that make sense? Well, no, you can't really, sorry, it's hard to see, but it doesn't really make sense because $20,000 per year means that their salary would be like shooting upward, like way past the graph, right? So what did I do wrong here? I forgot again about the order of operations. Division happens before subtraction, but what I really wanted to do was make sure that subtraction happens before division. Okay, so when you're working with Python, sometimes you get a right result, but sometimes you might get a result, but it might not actually be right. It pays to double check your work, and in this case, double checking my work showed me that I got something that was quite off. So parentheses, and I guess something that's more reasonable. So the first part of the graph, like the first slope part, doctors made about $900 extra per year. Then I'm going to look at the second part of the graph. So I'm going to take that, and in the second part of the graph, doctors made about $60,000 compared to $25,000, and this happened from 1976 to 1963. And I can see that the slopes are quite different. So after like 1965-ish, 63-ish, doctors started making a lot more money per year than everyone else. All right, cool. Let's move on. All right, so now I'm going to go back to, okay, I guess I'm going back to the demo. I'm now going to talk about numbers. So you may have noticed that some numbers in Python contain decimal places and some numbers don't. So for example, 2 plus 3 is 5, 2 times 3 is 6. But if you look here, 2 divided by 3 is 0.6. And this thing right here, this long thing that was 2017, had a 0.0 at the end. Okay, so there are actually two types of numbers in Python. There are what we call ints, or integers, short for integers, or floats, which is just another word for a decimal point number. So if I type 2 in my notebook, I just get the number 2. But if I do 2.0, I get 2.0. Now they appear differently because this is actually a float, and this is actually an integer. Floats always have a decimal point afterward. So if I do 2 point, it will appear as 2.0 because Python says this is a float, not an integer. Now they appear the same, but there are actually a couple of differences between the two. So let's talk about what those are. First of all, if I do division, no matter what kind of number I do in a division, I'm always going to get a float out as my output. If I do 5 divided by 7,000, I get something that looks like that. So this is a float that's pretty small, pretty close to 0. And when I divide by 70,000, you'll notice that Python switches to scientific notation. Okay, so this is pretty much the same thing as this, but with one extra 0 here. But once you get past a certain number of zeros, or get past a certain number of digits, Python will just automatically convert your number to look like 7.14 to the power times 10 to the power of -5. The numbers are actually the same. So if I were to type out 0.000 and then take that, these two things are actually the same. And Python will just display it like this, just to show me that, just to avoid me having to look through a bunch of zeros. I can also write out numbers in scientific notation if I'm feeling lazy and don't want to type out zeros. So I can just do that, and these two things that's another way of getting these numbers. Now, one interesting thing about Python, so let me do 1, 2, 3, 4, 5, 6, 7. So if I write that, Python will show me this as we've discussed before. So scientific notation. This and take it to the power of, say, 30. That's a really, really small number. And when it gets too small, Python just says it's 0. So Python can't keep track of numbers that are way too small. So do watch out for that. What happens when my numbers get too big? Well, if I were to take this and just paste in a bunch of zeros, so integers are actually okay. So integers, they can go up to any number of digits that you want. But floats, so if I were to take that same number and do 0.0 at the very end there, okay, I do 1 to the power of 165, but if I were to keep going, so let's keep adding zeros, okay, add a couple more, I get infinity. Okay, so floats have a limit on how big they can be on integers. The limit is pretty big. It's like 10 to the power of 308. So I wouldn't worry about hitting that limit anytime soon, but there is a limit in case you run into an infinity and you're wondering why I have infinity. Another thing I want you to be careful about is when I type in numbers, so if I type in a bunch of 6s here, and do 1, 2, 3, 4, 5, 6, 7, 9, what you'll notice is that past a certain number of 6s, Python just drops whatever I have left. Okay? And this is because Python has a limited, so your computer has a limited ability to represent numbers, to represent decimal numbers. Your calculator actually does too. So if you were to go to a graphing calculator and type in like a bunch of zeros and then like do 1 at the very end, your calculator would probably also round it to 0. That's because it's kind of like a fundamental or almost fundamental limitation of how computers are made, that there is some limit to how precise you can be. So if I were to do that, Python just drops off the end here. So when you get past like 16 decimal places or so, Python just chops it off. So what this means is that if I were to do this minus 0.6666, I'm actually going to get a 0. Okay? So this is a little bit unexpected, but you just have to remember that Python has a limited amount of numerical precision, is what we give a name to this. It can't represent that many decimal places, and so when we try to give it that many decimal places, it'll just chop it off and then do your computation. Okay, but do watch out for this, because let's suppose that I want to take the square root of 2. Okay, so if you remember from algebra, I can also take the square root of 2 by doing 2 to the power of 0.5 or 1/2. So if I run that, I get 1.414, etc. Because of Python's limited ability to represent decimals, if I actually take this and multiply it by square root of 2, you would expect to get 2, right? So square root of 2 times square root of 2 should equal 2. But if I run this, I actually get 2.0004. And that's because when you get down to the last digit and Python starts chopping off numbers, your results are going to be a little bit different than what they should be in theory. So this is actually, for our purposes, just 2. But you'll notice this as you work with numbers in the future, during your labs or during your homework. Sometimes you do some computation and you get something that looks kind of like what you want, except it has like 0.4 at the very end. Or it could be like 1.9999999, like 8 or something. So just remember that that's because of the lack of infinite numerical precision that Python has. And for our purposes, this is close enough that we'll just deal with it. Any questions so far? Yes.
Can you tell Python how many decimal places we want?
Yeah. So is Peggy? So Peggy asks, can we tell Python how many decimal places we want? We can. There's a function called round, and I'm going to be going over that tomorrow, I believe. So we can round a number and say I want to round to 5 digits. I want to round to 1 digit. So rounding is possible. Yeah. Yes. Name and question. Kevin.
If you put an int and a float, like you're adding them, does the int turn to a float, or
the float turn into an int, or something magical happens? Yeah, great question, Kevin. So why don't we try it out? So if I do 2 plus 5, I get an int. But if I make the 5 a float, I get a float. So in general, whenever I do some arithmetic and there is at least one float in there, the whole thing just becomes a float. Because Python is like, well, you probably want decimals, so I'm going to keep your decimals there. Great question. Okay. So one last note about the precision thing. So because of that, if I do subtract 2, what you'll notice is this happens. So because of numerical precision, I lose digits, and because of that, when I do 2 to square root of 2 times square root of 2 minus 2, I should get 0. Instead, I don't get 0. I get something that looks like 4.44 times 10 to the power negative 16. So it's really small. This is also caused by numerical precision, and we just treat that as 0. But do note that if you're looking for 0, it's not exactly 0, but for our purposes, it's so close to 0 that we just say it's 0, and we say it's because of the lack of precision. All right, so I think now is a good time for you guys to think about this on your own. So here's a discussion question. Oh, so let me recap first. So ints and floats. Int is an integer, float is a decimal. Okay. I said before that ints don't have a decimal point, and they can get as big as they can, big as they want. A float will always be shown with a decimal point. Python will also display floats using scientific notation, and we talked about floats have a limited size and they have a limited precision. So typically, after like the 15th or 16th digit of a decimal, we say those digits are like kind of trash quote unquote digits, because those could have been caused by the lack of precision. If you really want to be safe, typically we say something like 8 digits after decimal point is what we consider to be good or valid, and anything after that is not super reliable. All right, so here's the question. Rank the results in order from least to greatest. Try to do this without using your Python notebook. So think about this on your own for 2 minutes, and then I'm going to have you guys share the answer, and then I'm going to have you guys talk with your neighbor about it. So think to yourself first, and then we'll talk about it after. I also give you a hint. All 5 of these are different numbers, so there is an ordering to them. All right, so I can just take a poll of what you guys think is the biggest number and what you guys think is the smallest number. So if you can try to hold up the letter of the one that you think is the biggest, try to like make that shape with your hand. Okay, so show me what you think. Ready, set, go. Do it. So I see a lot of curvy hand shapes. So most of you guys think C. Okay, which one do you think is the smallest? Go ahead and make that hand shape. Okay, I see some O's, P's. Okay, great. Talk over your results with your neighbor.
Yeah.
All right, so what do you guys think? So A comes out to about, what is that, like 330 billion-ish. So that's A. B comes out to something like 500,000. So the reason why B is smaller than A is because 10 to the power of 10 is bigger than 3 to the power of 10 when you do the multiplication. C on the other hand is pretty big because we do the 10 times 3 first and then we do the exponentiation. D is pretty small, but E is bigger than D because when you do 3 divided by 10, you get something that's like 0.3, and then 10 divided by that is when you divide by. So if you like do the fraction, flipping thing, then you notice that the 10 goes up. Like when you divide by divide, it becomes a multiplication. So that's why E is bigger than D. Cool. All right. So now I want to talk about names, otherwise known as variables. So in Python, sometimes I'm doing some computation. I'm like blazing through some data, and I really want to save the results of my work somewhere. So I'm doing some computation, and I'm to say, oh, okay, I did this like 1 plus 2 plus 3 times 4 times 5, and I want to save that thing for later use. So that's where variables come in handy. Okay. So basically, when I want to save a result into a name, I write something that looks like this. Okay. So this part right here is the name of my variable, or the name of whatever the label I'm giving to my results. And here is the expression that computes the result that I want to save. Okay, so in this case, so this is called the name, and this is called the expression. And what happens is, when I run this in a notebook, you'll notice that normally when I do 2 plus 3 in a notebook, like 5 pops out. If I just write more than 1 equals 2 plus 3 in a notebook, I get nothing that pops out. Because statements don't become a value. It's telling Python to compute it and then save it for later, but don't actually show it to me. We call this an assignment statement, and just to one. So later on in Python, if I do like 2 plus more than 1, I will get 7. Okay. Now in math, typically we do something. Typically you've seen stuff like 1 equals 1, or like 2 not equal to 3. This is a little bit different than a mathematical equal sign. What it is actually saying is, Python, please compute this and store it for me. It's not saying to Python like these two things are equal to each other in the mathematical sense. It's really like an action of computing something and then putting it into a box for later use. Okay, so let me show you what I mean. So I can do what I did in the slides, which is more than 1 equals 2 plus 3. So this name, it can be almost anything that I want. Okay, so if I wanted to call it more than 2, that also works. I can do more than 3. I can even do more than 10, even though it's not actually more than 10. So you can name whatever you want. Variables can be kind of misleading, so I would suggest using good names. One of my friends uses like Pokemon names for all his variables, and reading his code is not that fun. Reading the code is not that fun. Okay, so try to be helpful to yourself. Okay, so more than 1 equals 2 plus 3. And if I want the results of that variable, I can take a look at more than 1 and run that, and I get 5. Okay, so right here is the assignment. I'm storing the results. Right here is grabbing the result back. So if I want to do some computation using more than 1, I can just do more than 1 times 2. And because more than 1 was 5 previously, what happens is when Python evaluates this, Python replaces more than 1 with its value, 5, and then does 5 times 2. So that's what happens underneath the hood. Now, you'll notice that this one doesn't print. So you notice that sometimes you can put more than 1 line into a cell. So each of these right here is called a cell in Jupyter. I can actually put more than 1 line. I can put 1 plus 1, and 2 plus 2, and 3 plus 3. What you notice is that only the last line prints. Okay, so Python actually computes 2, and it computes 4, and it computes 6. But the way it works is that, or the way it displays the result is that only the last line gets displayed. So if you're ever wondering why like these things don't display, it's because only the last line displays. And it seems kind of dumb, but it is useful when I'm doing something like this, which is more than 1 equals 2 plus 3, and then I want to display it in one go. So that way I can write one cell, assign, and then display the variable that I created. One little caveat with these variables is that when I do something, I can assign a variable equal to some other variable plus 1. So right now x is 4, and y will become 5. So if I write y here and display it, I get 5. If I change the value of x, just to convince you guys, x is 3, y is still 5. So when I change the variable of x, y doesn't know that x has changed. Y retains the value that it had before. Okay, so this is a little caveat. Do note that this happens, and if you're expecting it to change, it won't change. If you want to change, you're gonna have to make it change yourself and make it and do y equals x plus 1 again, and now y will have updated to the value of 4. Any questions about that? Yeah. Can we assign different types of values to the same name? So can I assign y equals to 4 and y equals to 8? What you're asking? So your name was Luke. So Luke asked, can I do y equals 4 and then y equals 4.0? Well, let's find out. It turns out you can, and what happens is Python will just save the last thing you ran. You have a box. Whenever you put something in the box, whatever was in there before gets kicked out. So if 4 was in there before, but I added 4.0, then 4 goes out, 4.0 goes in, your GPA is great. So, cool, good question. All right, a little bit of time left. Let's talk about an example. Oh, yes, sorry. Name and question?
If you were to go back and you were to put yourself and then enter in, like you already changed the value of your variables, but then you just went back and enter like the new line of code under what the previous value was, and you're going to go back to that previous value of the variable?
So great question. Your name was Emily. So Emily asked, so you're saying so right now y is 4, right? But before here, y was 5. So if I go here and do y plus 1, will y be 4 or 5? And will I get 5 or 6 as a result? So it turns out that when you run the code, Python looks at what's currently in your boxes. Okay, so the order in which the code appears here is not super tied to what's in my boxes. So I have a box for X, a box for Y. The last line of code that I ran put the value 4 into my box for Y. So actually, I believe it was 4.0, 4.0. So my box for Y currently contains 4.0. If I run Y plus 1, Python says, OK, grab the value of my current value of Y, which is 4.0. So it'll replace Y with 4.0, and then add 1 to it to be 5.0. So if I just to convince you, Y plus 1 would be 5.0. All right. So we do have to be a little bit careful because the order in which stuff happens is not necessarily like what your variable. So what your variable is here is not necessarily what your variable is here. It's actually just whatever was in your X and Y variables right before you ran your code. Okay. So if you really want to confuse yourself, I can reorder all these cells, and you have no idea what I did. So I can do this, and sorry, I can do that, and put that there, and then put this, and put that there, and then this, and put that there, and then now you're really confused. So basically, you can really mess yourself up. Okay. So typically, you want to be careful about running things in order and not like inserting cells in random places. And when in doubt, you can just try to like clear off some of the extraneous cells and just look at your values of X and look at your values of Y. And that tells you the most current up-to-date values of both X and Y, in case you ever get lost. Yeah, big question. Okay, a couple minutes. Let's talk about an example. So I want to talk about exponential growth. So if you recall, we typically call, when we talk about exponential growth, we also call it, we also use the term growth rate to say, oh, my water consumption increased by 100% every day, so now I'm consuming like gallons and gallons of water every day. So we say it's the rate of increase per unit time, okay? So basically, the formula and the way it works is if let's say, if I consumed like $1 worth of water yesterday, and I consumed $1.50 worth of water today, then we can kind of quantify or describe that growth rate by using this formula, which is X times 1 plus G. So X is my original quantity, so $1 worth of water, times 1 plus G, where my growth rate in this case would be like I grew my water consumption by 50%. So 1 times 1 plus 1 times 1 plus 0.5 is 1.5. So what happens here is that after, I'm gonna use a better example. Okay, so just to use like the simple example with the bank. So if I have $100 in my bank and I get like 5% interest every year, so I have $100 originally, and 5% interest means I'm going to multiply by 1.05 to get 5% interest. After like 5 years, the way to calculate how much money I have is to repeatedly apply that 5% interest, and the way I do that is by exponentiation. So if you do some algebra, what you can do is you can kind of move G to one side and solve for G, and what you get is to calculate the growth rate. What you do is you take the amount you have after. So if I have $200 in my bank afterward, and I had $100 in my bank before, I'd take that, divide 200 by 100, and then times 1 over t minus 1. I'm not going to go into that today, but this is just a formula. And the reason why I mentioned this is because in September of 2014, people were very frightened by this disease called Ebola. Okay? And President Obama was quoted, "It's spreading and growing exponentially." And this is a disease outbreak that is advancing in an exponential fashion. So what do they mean? It means that the rate at which the disease spreads grows according to like that multiplication equation that we saw before, which is quite scary because, as you know, if it continues growing at the exponential rate, soon the whole world will have Ebola and life will be pretty sad. So this is what. So at the time, this was a current rate of Ebola spread, and it does look like it's curving upward. And if it did continue at the current rate of exponential growth, by, let's say, I believe in a month's time, the number of people with Ebola will have gone from like 4,000 to 15,000, and then to like 1 million, and then it's bad news bears. Okay, so in reality, this is what happened. So it didn't actually grow at an exponential rate, but people were pretty scared about it. And do I have another time? Do I have time for a demo? 56. All right, I have 4 minutes left. I want to take you through another example of exponential growth, which is the growth rate of the federal budget. Okay, so in 2002, federal budget was 237 with a bunch of zeros afterwards, so they had a lot of money. Okay, in 2012, we got richer, so that amount of money grew to bad numbers. Let me just count the zeros here. 1, 2, 3. It was like $2 trillion, and then in 2012 we had about $3 trillion. Okay, and if I take the 2012 budget divided by the 2002 budget, what we can see is that over the course of 10 years, we have 42% more cash. Okay, good job, America. We can find out the yearly growth of our federal budget by following the same formula that I described in one of my previous slides. So let's just run through that now. I'm first going to convert this to trillions just because it's easier to work with. So I'm going to do that. And I'm going to do that. Okay, so just convert to trillions so it's easy to work with. And then what I can do there, what you notice is that the percent change is still the same. Okay, so whether or not I use like trillions or dollars, as long as the units of my two things are the same, I have the same growth rate. So finally, let's calculate the growth rate. So I just need to do this. And this is just plug and chug, but I'm just going to convince you that it works. And minus. So if I do that, what I get is G is equal to 0.1426. And I did that incorrectly. I was supposed to do exponentiation. So my growth rate was so my federal budget grew by 104% per year. But since it's a growth rate, we do subtract 1. So sorry, I should have been more clear. So typically the growth rate, we do subtract 1 to actually get a percent change. So the percent change per year was 3.6%. So, although it looks like we grew a lot over the course of 10 years, the yearly growth was actually not so great. But when you're working with trillions of dollars, 3% of a trillion is like a lot of dollars. I'll see you guys tomorrow. Thank you.